Now we get to the practical question. Once you know your load parameters and you know your performance targets, how do you actually design a system to handle the load and cope when load grows? The book starts with the classic debate, scale up versus scale out. Scaling up, also called vertical scaling, means moving to a more powerful machine. More CPUs, more RAM, faster disks. Scaling out, also called horizontal scaling, means distributing the load across multiple smaller machines, each handling a share of the traffic. Horizontal scaling is also called a shared nothing architecture, because each machine operates independently without sharing memory or disk with the others. A system that runs on a single machine is often genuinely simpler to build and operate. You don't have to worry about network partitions, coordination, or data consistency across nodes. But high-end machines become very expensive very quickly, and at some point the cost curve becomes brutal. Very intensive workloads often can't avoid scaling out. In practice, good architectures are not religious about this choice. They use a pragmatic mixture. Using several moderately powerful machines can be both simpler and cheaper than using a large number of tiny virtual machines. The right balance depends on your specific workload. One more distinction the book makes: some systems are elastic, they automatically detect load increases and add resources, then scale back down when load drops. Others are scaled manually by a human who analyzes capacity trends and decides when to provision more machines. Elastic scaling is useful when load is highly unpredictable, a viral social media post, a flash sale, where you can't know in advance when you'll need more capacity. But manually scaled systems are simpler and often have fewer operational surprises. Automation can go wrong in unexpected ways. Distributing stateless services across multiple machines is relatively straightforward. A stateless service is one that treats every request independently. It doesn't need to remember anything about previous requests. Serving static files, running a computation, rendering a page, all stateless. You can put 10 machines behind a load balancer and they all handle requests identically. Stateful data systems are a different story entirely. Taking a database from a single node to a distributed setup introduces a huge amount of additional complexity. Now you have to think about, where does each piece of data live? What happens if a machine goes down while a write is in progress? How do you ensure two machines don't serve conflicting answers to the same query? What does consistent even mean when data is spread across nodes? These are hard problems. Because of this complexity, the conventional wisdom for a long time was, keep your database on a single node and scale up. Scale up until the cost becomes prohibitive, or until your high availability requirements force you to go distributed. That wisdom still has merit today. But as tools and abstractions for distributed systems improve, and they have improved dramatically, this calculation is shifting. It is conceivable that distributed data systems will become the default in the future, even for applications that don't handle particularly large volumes. The rest of this book is largely about understanding those tools and trade-offs. Here is one of the most important pieces of practical wisdom in this entire chapter, and it's worth quoting almost directly. The architecture of systems that operate at large scale is usually highly specific to the application. There is no such thing as a generic, one-size-fits-all scalable architecture. The book calls this non-existent thing magic scaling sauce. Everyone would love a silver bullet, a single architectural pattern you could drop into any application and have it scale effortlessly. It doesn't exist. The problems vary too much. Your bottleneck might be read volume, or write volume, or the amount of data to store, or the complexity of that data, or your response time requirements, or your access patterns, or, most commonly, some mixture of all of these. To feel the difference, a system handling 100,000 requests per second where each request is 1 kilobyte looks completely different from a system handling 3 requests per minute where each request is 2 gigabytes, even though both systems have the same total data throughput. Same throughput, completely different architecture. Here's the dangerous implication for startups and early-stage products: an architecture built around assumptions about your load parameters is only valuable if those assumptions are correct. If they turn out to be wrong, the engineering effort was at best wasted, and at worst locked you into an architecture that now actively hinders your ability to iterate. In an early-stage startup, being able to move fast on product features is almost always more important than scaling to hypothetical future load. Build for the scale you have, with an eye toward the scale you'll have soon. Don't over-engineer for a scale you might never reach. The good news: scalable architectures, even though they're application-specific, are built from familiar general-purpose building blocks arranged in well-understood patterns. That's exactly what the rest of this book teaches: the building blocks and the patterns.